MEDpf software library for modeling and simulation of solar desalination systems. www.reslibrary.com.
Hi everybody, Professor Mohammed Sharaf with you. Today we are going to talking about solar thermal power for multi-phase distillation per-feed configuration with mechanical vapor compression desalination processes by utilizing organic Rankine cycle. What is the main concept? How can we run our model? Let's see. The main concept: solar thermal power is directly transmitted from the solar collector field by collector collector by boiler heat exchanger unit toward this organic Rankine cycle. We are going to use or utilize toluene organic as a working fluid. The process is implemented according to the operation of parabolic trough field with terminal VB1 heat transfer oil. Intermediate unit, it's a boiler heat exchanger for thermal power to be transferred to organic Rankine cycle. Organic Rankine cycle, it's a turbine unit, recuperator, because it's a positive slope on TS diagram, recuperator unit, and condenser and pumping system. Sure, MEDpf-Mechanical vapor compression is used for thermal desalination processes. The turbine unit is going to develop its power to the mechanical vapor compression and pumping system. Mechanical vapor compression desalination process is most attractive among various single-stage desalination processes, even single-stage mechanical vapor compression. The mechanical vapor compression system is compact, confined, and doesn't require external heating source, which is opposite to thermal absorption or adsorption vapor compression. System is driven by electric power transmitted from the turbine unit. Therefore, it's suitable for remote population areas with access to power grid lines. Around it's produced around 5,000 up to 10,000. Another advantage is the absence of the down or end condenser if you compare against thermal vapor compression, and cooling water requirements and so on. This is because the compressor operates on the entire vapor formed within the system itself. Okay, this is our cycles that we are going to explain today. As you can see, we have solar field. This is terminal heat transfer loop through the solar field, pumping unit with a terminal, and we have organic Rankine cycle represented by a toluene working fluid. We have this is organic Rankine cycle, and we have a desalination process itself. For toluene, we have we have intermediate unit. It's boiler heat exchanger in order to transfer the massive thermal load from massive thermal power from solar field to operate organic Rankine cycle toluene. Toluene, because it's a positive slope on TS, so there is no need for superheat. As a maximum temperature up to critical temperature up to 380 degrees or 318 degrees Celsius. And it's quite it has a massive performance on the turbine unit and with compact turbine units and so on. Turbine unit is going to deliver the power for the compressor, the vapor compressor. The rest of steam, exhaust steam, is going to transfer, because it's still in superheat region, transfer the thermal energy as a recovery. This is a recuperator unit to the stream of retained stream from the pump going to the boiler heat exchanger unit in order to make this some kind of regeneration. For the MED, this is our MED unit. There is no end condenser. We are going to eliminate feed heaters or brine feed heaters. The feed seawater is going to gain some of regeneration energy or some of the recovery energy from the condenser unit in order to condensate, make some condensation of the turbine working fluid, and gain some heat before going to the MED process. Okay. For MED, mechanical vapor compression, we are going to eliminate plate heat exchangers or surface heat exchangers or the end condenser by the using of the condenser unit of the organic Rankine cycle. And this is the mechanical vapor compressor, which is will deliver the electricity from the turbine unit. So the distilled water, you are going to assign this parameter. You are going to assign this parameter in order to reconfigure or recalculate the load on the mechanical vapor compressor. And the load on the mechanical vapor compressor will demand its operational state from the organic Rankine cycle, especially turbine unit. And the turbine unit is going to be operated by the intermediate unit of the solar field. Okay, this is our process on TS diagram. As we can see here, this is for turbine. As you can see here, this is condenser pressure. It's around 35 degrees Celsius, and we have here pumping outlet conditions. It's 37. Therefore, we're going to increase the inlet pump stream going to the boiler heat exchanger by the utilizing of recuperator unit. So we are going to raise up the temperature of the outlet stream of the pump from 37, 38 up to 100. It's sure it will preserve much energy and so on. Therefore, this is the outlet turbine unit condition. It's around 300 for the turbine. Okay, and this is 138. This is the outlet turbine condition. This is outlet turbine condition, and therefore, after the recuperator unit, the temperature will reach 58 degrees Celsius before going to the condenser unit, and so on. Seawater is normally from it's around 25 and so on. This is some input data or design points. For solar field, we are going to assign the ambient temperature, outlet temperature of the solar collector, some efficiencies, effectivenesses, condensation temperature 35, quite suitable for the condenser unit. And we have recuperator efficiency, boiler heat exchanger efficiency, boiler inner tubes, some design inputs, seat water temperatures around 25, compression ratio is 2. This is thermal vapor and this is mechanical vapor compression. And this is feed salinity, brine blow down salinity, number of effects we can increase, number of effects, and mass flow rate of the productivity stream, plant life, and some calculated units. Okay, how can we run our model? We are going to discover design aspects, some performance analysis, energy stream, enthalpies, entropies, pressures, exergy, and thermoeconomic streams. Okay, our model should be appear like this. Okay, going to your destination folder. Okay, choose your folder. Double click on your model or drop it here. Okay, and should be appear like this. Okay, This is some cases study, some inputs parameter you can utilize. Let's go and assign some parameters. Okay, for solar radiation, I'm going for 650. Ambient temperature, I think it's 25. It's fine. Outlet solar field temperature, top solar field temperature 350. It's okay. This is outlet turbine conditions. It's around 30, as was said before. Design. Okay, let's go for example, for 5,000 or 3,500 meter cube per day, and let's see if we run our model. But first we have to assign some individuals for each unit. This is parabolic trough. We can assign hydraulic mass flow rate, collector widths, if you are going to use glass system or Euro trough. And this boiler heat exchanger, this is effectiveness. Some inputs I'll give it. This oil heat transfer unit. This oil heat transfer unit for pump. I mean pumping unit is efficiency. It's okay. For turbine, it's efficiency. Okay. And this turbine unit efficiency and generator efficiency. It's okay. Recuperator unit effectiveness, okay. A condenser unit, yes. For condenser, we are going to. This is condensation temperature. I think it's 35 is quite interesting. Seawater temperature is 25. Good. Some design aspects for the condenser, and this is cost analysis block and. This is performance block. MED. For MED, steam temperature. You can assign your steam temperature. Okay, I think 60. It's like the example. Okay, 60. It's okay. Blow down temperature. It's 46. It's okay. MED number of effects. Two effects. Let's start two effects. Compressor design. We can assign compressor adiabatics. Index gamma and performance. Some performances: compressor efficiency, pump efficiency, brine pump efficiency, distill pump efficiency, and seawater pump efficiencies. Okay, let's hit run. Okay, you can discover some inputs, some some outputs: gear ratio, exergy of total feed. Specific solar area. You can go for performance block, yes. The specific solar field area, specific power consumption, total irreversibility, total exergy efficiency, and so on. This for parabolic trough, as you can see here, pressure, enthalpy, area, total area, collector total length, number of loops, number of solar collectors. Okay. This is boiler heat exchanger. You can discover outlet stream going for returning back to the parabolic trough and the turbine unit. This is oil, heat transfer oil enthalpy, transfer oil temperature. This is the input temperature to the solar field, 150. In order to rise it up to 350. This is enthalpy of the oil, entropy of the oil, and pressure. This is outlet vapor pressure going to the turbine unit. Okay, this is going to as the turbine unit, and this is pressure inside the solar field. It's quite comfortable for the tubes. Mass flow rate through the solar field, effective area, and so on. And thermoeconomic analysis, sure. Okay, this is pump. This is a heat transfer oil pump. The pump is going to consume around 13 kilowatts. Turbine units. Okay, so this power is 1,700. It's a power from the compressor, pumps, and so on. This value, it's the value that the turbine or the organic Rankine cycle it should provide, and this is total mass flow rate. This is outlet temperature of from the turbine is 138, entropy, reversibility, cost of the power, and so on. Recuperator unit, okay, this is a recuperator unit. This is to the evaporator inside. This is pump stream. This is for the condenser enthalpy, and this is the stream for going to the condenser, and this is 101 is the preheated feed, the preheated stream from the pumping unit. Okay, this is the preheated feed from the one around 100, and so thermal energy, exergetic stream areas, and so on. And this is condenser unit, condensation temperature, pressure. Okay. This is pumping from, this is Tolwyn pump. It's around 47 kilowatt consumption. This is MED. Let's see for MED. Okay. This is our compressor. Our compressor is going to consume around 1,400 kilowatts of power in order to desalinate 3,500. This compression ratio is around 1.436. Okay, and this is we are going to utilize two effects. This is effect one, thrust effect for distal profile, brine profile, salinity profile, and so on. We can draw some the profile if you are going to workspace. Let's go to the workspace. Yes, as you can see here, this is the area profile. You can draw it. Okay, and this is the profile. We can draw bars because it's two effects. Okay, let's go for more than. I'm going to assign, let it be for MED design. I'm going to, it's matrix, 4 effects. Let's go for 4 effects and see what is going on. Logging into MED and hit run. Okay, excellent. This is, sure, this is steam temperature was assigned. And this is preheated steam from the condenser unit. This preheated steam from the condenser unit, as you can see here. This stream is 25, and it's preheated up to 31. Okay. As you can see here, this is effects. Let's see the effect of okay, the compression ratio. So this compression ratio is increased, and the power consumption is reduced because we increased the number of effects. Okay, let's see some effects on the power by changing the system productivity. As you can see here, I'm going to change the system productivity for MEDpf 5000. Going to MED, and here, as you can see, I'm going dynamically, infinity of time. Okay, let's begin from 1000 or 1000. Okay, and let's hit run. I'm sorry. Let's go for 1000. Let's hit change. Okay, I'm going to change productivity and watch the effect on the power. Okay, okay, increasing the productivity sure will increase the power. Okay, as you can see here, changing the productivity will change everything. Okay, up to suppose it's 1 megawatt. Sure, this value are going to increase everything because it has a massive effect on the flow rate through the cycle itself. So increasing the power, I'm going for Suppose I'm going for 10,000. Let's see. Okay, this is the power for 10,000 meter cube per day. As you can see here, we can sure reconfigure this inputs. Let's stop. So if you are going to increase the compression ratio and reduce the power, you have to change the number of effects I'm going for. But after this one, I'm going to discover the effect of number of MED units. Okay, as you can see here. Okay, let's draw some parameters like total irreversibility. Okay, increasing the mass flow rate would increase the total reversibility to the system. Let's see, working. This is the compressor power. Compressor power. This is when I enter 10,000. 10,000. This from 1,500 up to 10,000. Massive increase, and this is I'm going for total hour. This is hourly cost parameter. Okay, this is hourly cost increased massively because you increased the total system flow rate and so on. Okay, let's changing the number of effects up to 8 effects and see the effect on the power. Okay, this is 8 effect. I'm going to watch the effect on the compression ratio, specific power, compressor power, and the total power should be delivered to the compressor unit. Okay. Okay, so it's dropped from 3,000 plus to 1,900. Compression ratio is increased from 1.8 up to 1.7 up to 1.8, and this is effect by effect. As you can see here, prime profile, salinity profile. This is temperature of blow down profile per each effect. Vapor profile, distillate profile, and pressure profile through each, and this is the gear ratio because it's the operation of 8 effects, so it's around 7.5. Area profile for each effect, length. This is a pumping unit, power consumption per each pump. Let's see if we, yes, this is thermoeconomic product cost. Thermoeconomic product cost, it's around 0.8 gigajoule, US dollar per gigajoule. Okay. Okay. The conclusion is we have MED-mechanical vapor compression. It's ready to be used by utilizing solar organic Rankine cycle, especially Tolwyn, after many of research activities about this. And you can assign some inputs, some operating conditions, and you can discover the performance of systems, thermoeconomics, exergetic and energetic streams. And it's sure you can compare against conventional MED. You can compare against conventional mechanical vapor compression. Okay, finally we are glad to say that we have many other solar desalination plants you can download and discover, especially if it's used with geothermal energy by utilizing concentric solar gas engines as a power source, It's very impressive to discover such configuration. Finally, we have to say thank you for watching. Please like, share, subscribe. Thank you very much.